So I got to admit, I hate that title. That's why I changed it. I'll be talking with you all about kind of a journey we've gone on over the last decade. I mean, Matteo and I have been working on in situ spectroscopy our entire professional careers, I think. Um, I'll kind of give you our perspective of a partnership between my institution, which is a nonprofit, the Soil Health Institute based out of the United States, and our commercial tech to market partner, Yardstick. Um, Terrible title notwithstanding, Yardstick are a great partner for us. And I kind of want to give you a little perspective on our relationship because I think it informs kind of the credibility of some of the stuff we'll be talking about today. So, like I mentioned, Soil Health Institute, we are a registered 501c3 nonprofit in the United States. Um, our partner here is Yardstick. They are a for-profit public benefiting company, PBC. Um, we don't have any sort of commercial relationship with Yardstick outside of our collaborative research work. So Soil Health Institute does not receive any profit share, or we have no dividends or stakes in Yardstick as an entity. So um, I think that's really important to say because a lot of what I want to establish here is the credibility of the technology. And I'm not here to sell you on Yardstick as a tool or a technique. I'm here to present some really interesting science that I think should interest everyone in the room. Um, so kind of that's sort of my like caveat to what everything I'm going to say. Um, don't trust anybody with a microphone and a slide deck, I guess. So what is Yardstick? Oh, the Yardstick is a handheld soil spectroscopy probe. See if I can get this video to work. Oh, there's the mouse. There we go. All right. It's a very small, compact, visible near-infrared spectroscopy probe, specifically designed to measure soil carbon stocks in the sort of use case of stock quantification to support MRV platforms or MRV efforts, either through registered soil carbon offset methodologies or insetting offsetting approaches. So the operator starts the probe, drills it into the ground, and as it's drilling into the ground, it's collecting a bunch of visible near-infrared spectra, as well as some depth information that we can then use to compute the soil organic carbon stock in a field. So big advantages of this. One, it's pretty fast. So this is, the whole video plays in under 30 seconds. We get to the bottom of the core and you can just pull it out really quickly. So it's a very fast measurement technique. All of the data we're collecting are in situ. So essentially, once the probe is calibrated for a given domain, we can go and we can put the probe wherever we want and measure soil organic carbon stocks. Very cheap, very quickly. We don't have to take samples back to the lab. So that's a huge benefit in terms of scaling and generating carbon stock data across really large scales. Okay. So when I talk about large scales, I think that's important to recognize that scale is really important from a commercial soil carbon stock monitoring perspective. If you are a carbon developer, there's a couple folks in the room in this industry. You want as big a project acreage as possible. You want that for two reasons. One, the bigger your project acreage, the more carbon credits you can generate. Two, you see a lot of benefits of scale as you scale up your project size. Uncertainty has you have some benefits to your uncertainty instruments, as well as you benefit from initial program investment, right? You invest once and you can use it on as many acres as possible. So one of our learnings as the Soil Health Institute working with commercial partners here is that when we think about scale as researchers and scientists, we're often not really thinking about scale the way a commercial entity would. So what I'm going to present to you here is a very small pilot of a commercial project. So these are, orders of magnitude smaller than a real commercially developed pilot where we've tested the Yardstick probe. So our two project sites, one in Minnesota in the United States and one in Kansas in the United States. So each of these represent a collection of commercial corn and soybean farms, highlighted here by the dots. And they're, like I said, relatively small from a carbon development perspective, 6 fields and 4 fields respectively. So in each of these sites, We use the stratified random sampling approach to collect a series of calibration and validation cores, which are denoted by the numbers here. So 44 and 35 for validation calibration respectively in Minnesota, and 56 and 35 val-cal for Kansas as well. So at each of those calibration sites, we collect a yardstick measurement and a separate soil core for calibration. And then we also collect a conventional soil stock core. So kind of highlighting what the calibration process looks like. This is a really ridiculous cartoon of the probe tip. Here is the spectral window. So if you're familiar with spectroscopy tools, there's always some sort of optical interface between the soil and the probe. So there's a light inside the probe, it emits a light onto the soil, and the light is reflected back into a fiber optic, and we see a sort of visible near infrared spectra that a lot of folks in this room who've done spectroscopy are familiar with this. I like to call that a soil fingerprint for the non-pedometricians in the room. We also collect a co-located soil sample for a proportion of those validation sites, or calibration sites, excuse me. And from that, we can use the spectral information along with the soil sample to develop a soil carbon stock prediction model, and use that to predict soil carbon. So when we take a soil sample, or when we take the probe to a new location, we can drill it into the ground. As long as that model's already there, we can predict the soil carbon stock. Ultimately, the whole aim of all of this isn't to think about points, but to think about stocks across projects. So we'll talk about project stocks in a minute. I'm getting ahead of myself. So here's results from the actual probe calibration for our two pilot sites, Minnesota and Kansas. So what you're looking at here is lab measured carbon stocks. So these are the actual measured samples at our validation sites. So these are independent of model calibration. And then on the y-axis are the VisNIR calibrated stocks. So these are stocks predicted with the spectral probe. The orange line here represents the 1-to-1 line. So in a perfect scenario, we saw a couple really great graphs from mid-infrared spectroscopy in Africa. Those points, man, they lined up right along this line. You'll notice our visible near-infrared data a lot noisier, a lot less precise. So we see the blue line is the trend line for our predictions. And in both cases, Minnesota and Kansas, predictions are falling below that line at high carbon contents. So essentially, when we have high carbon stocks, we are under predicting the amount of carbon consistently from site to site. I'll also note some of the performance metrics here. Spectroscopists in the room will be displeased with these R-squared values, relatively low in the spectroscopy sense. Visible near-infrared spectroscopy, I would prefer to see R-squareds of around 0.8 to really feel confident in the models. But this is the reality of using in situ data in the field, rapid measurements. We lose a little bit of precision compared to MIR predictions. I'm not going to bury the lead here. Doesn't really matter at the end of the day. Okay, so all we've talked about is points, measuring single points. That really doesn't matter for a project developer. A project developer wants to know, in my collection of fields, how much carbon is there? So if I look at the carbon stocks at individual points, I need some sort of statistical framework to aggregate that point measurement to a project level stock. How many tons of carbon are in upper 30 centimeters of all of these fields? So we have two approaches for measuring carbon stocks. On the left is what I'm calling conventional stocks. If you were to go out and do a carbon inventory today using existing tools, this is the pathway you generally would follow. On the right-hand side of what we're calling probe stocks, you'll notice there's a couple more bullet points because it's a little bit more intensive in terms of the number of steps we take, but we end up at the same place. An estimate for a given project area, how much carbon is in the upper 30 centimeters, and an estimate of our confidence about that estimate. So conventional stocks, first step, right? We measure soil organic carbon stocks at each validation site. Every soil scientist in the room has done something similar to this. You take a soil sample, you measure the bulk density, you measure the carbon concentration, you compute a stock. And you do that a bunch of times, ideally in some sort of stratified random sample, which is what we did here. Next, you compute a stock mean and variance for each strata. This is really common again in the MMRV space. We have a designated way of partitioning the landscape. And for each of those strata, we can calculate their statistics. And then following the guidance of the Climate Action Reserve's soil enrichment protocol, we can estimate a project level stock mean and variance from area weighted strata level statistics. So if we know the variance and the mean of each strata, we can then impute what the project level stock mean and variance would be. Man, I am not a statistics lecturer. So probe stocks, alternative pathway here. Instead of collecting a soil sample, we use the yardstick probe to measure a carbon stock or predict the carbon stock at each point. We use our calibrated model to predict the carbon stock using the spectra. Again, this is without any laboratory data in this actual way here. This is all based on proximal predictions. The next step is to use a conformal prediction to estimate the distribution of probable soil organic carbon stocks at each point. I'm not going to get into conformal predictions. There's a lot of great literature out there. Essentially, it allows us to estimate our uncertainty at any point based on our calibration model. Next, we use those point level distributions to compute a strata level mean and variance via a bootstrapping technique. And then finally, using the same techniques we used here, we take those strata level statistics and scale them up to a project level measurement. That is a lot of nuts and bolts. But essentially, the takeaway is actually really exciting. So what you're looking at here are predicted stocks for the two project areas. So this is that question answering how much carbon is in my collection of fields. And you'll see in each of these graphs, which each represent one of our project domains, Minnesota and Kansas, we have the total tonnage of carbon on the x-axis. That's what the developer really cares about. How much carbon do I have? And these are probability density plots. In the blue is our conventional stocks. So these are the stocks measured the traditional way, taking a physical soil sample, calibrate or measuring the carbon, measuring the bulk density, measuring the stock directly. The orange line is the probe predicted carbon stock. So this is using visible near infrared spectra only. Important thing to point out, if you remember from our previous graphs, each of our spectral measurements had a bias or under prediction at high carbon stocks. What we see when we go and scale these measurements to a project domain, the amount of variability within strata and across the project tends to not matter as much from a stock prediction perspective. So we see that both the probes and the conventional stocks are actually quite aligned. There's no statistical difference between these distributions in terms of means. So we have a really reasonable estimate of carbon stocks that is kind of congruent with what we see with conventional measurements. So to kind of wrap up, yardstick can predict soil organic carbon stocks. Kind of. It does a pretty good job in a calibrated domain. Takes a lot of calibration work, but we can predict carbon stocks with moderate precision. However, when we use those probe predictions to quantify carbon stocks for a project domain, we see that we have really comparable estimates of the amount of carbon in that area. And then lastly, I want to highlight that despite probe under prediction at high carbon stocks, that does not necessarily lead to a systematic bias in our probe predicted project level stocks. So again, one of the things I think that's important to think about in the proximal sensors world is what is the use case you're trying to apply that tool for. We often find that spectroscopists, I think that spectroscopists get very focused on having the best performing models, driving down their RMSE and driving their R squared up as much as they can. And we've had several conversations over the last couple of days around how precise do your data really need to be. And I think one of the takeaways for our work in this space has really been, point level data doesn't necessarily have to be as precise when we're dealing with large commercial scale geographies. One of the reasons that companies like Indigo Ag have been successful in generating soil carbon credits is because they develop very large projects that have all of those benefits of scale, reduction in uncertainty, benefits of costs. So that's the end of my talk. I will say I did bring one of the yardstick probes with me in the back, so I'll have that out during the coffee break. So please come stop by, pick up the probe, push the buttons, let it spin around. It's a really cool device that I think a lot of people should be excited about.